In this presentation, we'll introduce the everlasting exponential signal e to the st. Now this signal, like the impulse signal, is not physical, but it's still very important. S in the e to the st is a complex variable. It has a real part and an imaginary part. The real part is denoted sigma. The imaginary part is j omega, where j is the square root of -1. The reason why we use j rather than I is because this field was founded by electrical engineers, and they wanted to reserve I for the current. We'll put this definition for S into our formulation e to the st and evaluate it. So e to the st is e to the quantity sigma plus j omega t. Separating this into parts, we find it's e to the sigma t times e to the j omega t. And from Euler's equation, we know that e to the j omega t is cosine omega t plus j sine omega t. So e to the st is e to the sigma t times the quantity cosine omega t plus j sine omega t. We note the fact that j sine omega t is not a real valued signal. However, e to the sigma t and cosine omega t are real valued. Now let's introduce the complex conjugate of the variable s. A complex conjugate is where we take the imaginary part and we reverse its sign. So the complex conjugate, denoted s star, is sigma minus j omega. Looking in the complex plane, we can plot s at sigma on the real axis and omega on the imaginary axis. S star would then be plotted at sigma on the real axis and minus omega on the imaginary axis. So the conjugate point for S is a point that is a mirror image reflection about the real axis of the point S. The signal e to the s star t can be evaluated as e to the sigma t times the quantity cosine omega t minus j sine omega t. Again, this comes from Euler's formula. So we found that e to the st was e to the sigma t times quantity cosine omega t plus j sine omega t, and e to the s star t was e to the sigma t times the quantity cosine omega t minus j sine omega t. So if we add these two signals together, we'll get the plus j sine omega t and the minus j sine omega t terms to cancel out. Therefore, 1/2 the quantity e to the st plus e to the s star t is e to the sigma t cosine omega t. And we note that that now is a real valued signal. So this formula allows a linking between these imaginary signals, or complex valued signals, and real valued signals. Now, note that e to the sigma t is going to be a function that will either be flat if sigma is 0, increasing if sigma is greater than 0, or decreasing if sigma is less than 0. So it's the real part, sigma, that controls the growth of e to the sigma t. The cosine omega t, of course, doesn't grow. It just oscillates, and the frequency of oscillation is the imaginary part, omega. So what does e to the sigma t cosine omega t look like? Well, it depends upon the value of the real part, sigma. If sigma is greater than 0, this is an oscillating function, oscillating at frequency omega, that is increasing. If sigma is equal to 0, it's an oscillating function with constant amplitude. And if sigma is less than 0, it's an oscillating function whose amplitude is decreasing with time. What does e to the sigma t cosine omega t look like if omega is 0? Well, cosine omega t would then be 1 for all time. And so e to the sigma t cosine omega t would just be e to the sigma t. It wouldn't oscillate. It would simply increase or decrease, or if sigma was 0, it would stay constant. So depending upon where the point S is in the complex plane, we'll get different signals for e to the sigma t cosine omega t and for e to the st. If point S is in the left half of the complex plane, that is, if sigma is less than 0, the signal will have decreasing amplitude with time. If the point S is in the right half of the complex plane, that is, sigma is greater than 0, the signal will have increasing amplitude as a function of time. And if the point S is on the imaginary axis, it will have constant amplitude as a function of time. To close this introduction to the everlasting exponential signal, I want to compare it to the causal exponential signal. The everlasting exponential signal is given by e to the st, and it's an everlasting signal, so it's always doing something. It starts at time minus infinity. The causal exponential signal is given by e to the st times u of t, and the presence of the u of t means that it doesn't start until time 0. Because u of t doesn't start until time 0, it has a value of 0 before time 0. And so it converts the e to the st into a causal signal. If we graph the two signals, the everlasting exponential signal is shown on the left, and the causal exponential signal is shown on the right. In both cases, the graphs were done for omega equals 0.